Okay, so this is going to be the summary of some parts. Actually, I think for the exam I will include material from this point correlation, right? So here I'm discussing only some of the mathematical stuff. What the other things if you can read. So let us look at what correlation means. We use usually the word correlation when you want to describe the relationship between two numerical variables, right? When you have two numerical variables, and if you want to see whether there is a relationship, if there is a relationship, what kind of relationship and so on, then usually talk about correlation. But sometimes we want to look at whether there is a relationship between some categorical variables also. In that kind of situations, we use the word association. So the word association and correlation roughly means the same thing, but it is usually used in two different contexts. Right? When you want to look at the relationship between qualitative variables to qualitative variables, you talk about association. But a more technical word like correlation is used when you describe the relationship between two numerical variables. So whenever you want to explore the relationship between two numerical variables, of course you have to have paired observations, right? So if you're collecting data, say for example individuals, there are two variables x and y. So from each person you have to have a x value and a y value. So there's a pair. From the other person also, then you have to have x and y. So it says the association. Generally, the word association is used for all cases, but particularly when you have quantitative variables, we call that association a correlation. Right? So one thing we have to, many people do sometimes is just calculate when you have numerical variables, when they have paired observations, they just calculate the Pearson's correlation coefficient, right, directly, and then look at the value of it and whether it is close to the 1 or 0, and depending on that they claim that there is a relationship or not, and whether the relationship is strong or not. But that is a wrong method to do, right? Wrong thing to do. Because the interpretation of this correlation coefficient, Pearson's correlation coefficient, actually depends on what kind of relationship actually has. So therefore it's best to always, when you look at the relationship between two numerical variables, it is best to first explore the relationship graphically, right? So the best graph for that purpose is the scatter diagram, right? So you just plot your paired observations on a XY axis, right? The Cartesian axis, and then you can see whether there is a relationship, right? So whether there is a relationship, or if there is a relationship, whether that relationship is a linear one or non-linear one, right? Whether the relationship look strong or weak. So many things can be seen from a graph. Also whether there are outliers can also be seen, right? Because these are important things when you are interpreting the correlation, right? So therefore graphical inspection is essential actually before computing any numerical summary like Pearson's correlation coefficient. Right. So for example, these are scatter plots, but so you can see that in different graphs the relationships are different, right? So if you don't look at any of these graphs, for example, a person can calculate R for all these things. So for example, here you can calculate R, you can get a value. For this also you can calculate R. For example, if you calculate R for this case, you might get a value close to 0, and then one might say there is no relationship. Right? If you say like that, then this is wrong actually. There is a relationship here. Right? It's a very kind of a very strong and mathematical relationship. But what is why correlation will be close to zero is because there is no linear relationship, right? So therefore, looking at the graph is important. Right? So you should calculate correlation coefficient only for this kind of graphs. Here, when you look at from the graph itself, it is clear that there is no relationship, linear or any other relationship. Right? Here, there is a relationship, but it is not linear clearly. And it's a relationship, it's not linear. And here also there is some relationship, it's not linear. So by looking at these things, if you want to talk about the relationship, well, for these you will have to use some other method, like not Pearson's correlation coefficient. But for these, you can measure the strength of the relationship, the linear relationship, if you calculate the Pearson's correlation coefficient. So therefore, exploring the graph is very important. So once you think that there is a linear relationship, of course you can calculate R, and then R, the value of the R, will give you mainly two things. The direction from the graph itself, you can see the direction, whether it's a positive relationship or a negative relationship, and then also it gives you a measure of the strength of the linear relationship. So for these you will get different values. Depending on that, you will be able to mention the strength, and you can compare the strength of linear relationships in two situations also. In addition to that, another advantage of having a scatter plot is you can explore whether there are outliers, right? So for example, in this graph there are three outliers, right? This observation is outlying with respect to its y values, right? This observation is outlying with respect to x value, right? Because this is the general or the bulk, the reason range for the bulk of x values. This is completely different from that. Therefore, that observation is actually its value of y is somewhat close to this one, but value of x is completely out. So it's outlying with respect to x. This one is outlying with respect to y. This one is outlying with respect to both x and y. But as far as the if you ignore these ones, for example, these sets show you there is a strong linear relationship. But if you include, if you don't look at the graph, you will be calculating R with all of these. Then it will give you a completely distorted picture. Right? Actually, in this case, if you include these ones, there will be an effect from this outline observation. There will be a effect from that, but this will not make a big problem because it's in the same direction as this one. Therefore, R will not be affected that much from that observation, even though it's an outlying observation. Right? So therefore, these kind of observations are sometimes called they are outliers. In addition to that, they are influential outliers. Influential, right? Even though this is an outlier, it is not an influential outlier as far as R is concerned. Right? So if you have maybe this only one or maybe several, before you calculate R, first of all you have to edit your data. If these kind of observations can arise, for example, due to recording errors or some other errors also, if that kind of observation has occurred due to an error, of course you have to correct them before you calculate R. Right? But if actually this was a real observation, in that case R is not suitable to calculate, right, for this. So then we'll have to do something else to, or maybe at least describe what is happening here, right, without calculating R. Right. So anyway, if there is a linear relationship and if there are no outliers, Then of course you can use this quantity called the Pearson's correlation coefficient, or sometimes called Pearson's product moment correlation coefficient, to get some idea about the correlation or the association between two numerical variables. This is actually an estimate of the population correlation, right? There will be a certain amount of association in the population between two variables. This is simple R. It's an estimate of that quantity, right? So that's what we usually calculate. So you can see that R actually is a product of standardized values, right? So you have x value and y values, x1, y1, x2, y2 and so on. So for each pair you can calculate, for example, is it x1, is it y1, is it x2, is it y2 and so on. You get these values. So this is zx, this is y, like that. So that's the product of standardized values, and then calculating the sum of those products and taking the dividing by n, that is taking the average. Right. So you already know that R, whenever we calculate it, it should be between -1 and +1. -1 and +1 are the extreme values. Those are not occurring in practice usually. They are very rare if that is in a case like that. So generally it will be between those two. Right? But if the value R is close to +1 or -1, then we interpret it as a strong linear relationship. Depending on the sign, we can say whether it's a positive strong linear relationship or negative strong relationship, linear relationship. The word linear is very important interpreting R. If the R is equal to 0, again it may indicate a weak or no linear relationship, right? Because some people make a mistake here. They say when R is equal to 0, there is no relationship. That is wrong. R equal to 0 indicates there is weak or no linear relationship. But there can be some other very strong relationship as well. Okay, a strong relationship may exist even in the correlation coefficient is close to 0. This one example that I can say here. If you calculate R will be very close to 0, but there is a very strong quadratic relationship. And the other thing is correlation coefficient, especially when you just calculating R, you don't have to worry too much, but sometimes we are interested in testing, going beyond just calculating. We want to make some inference regarding the population correlation coefficient. Right? So usually we did on the population correlation coefficient between x and y by rho. We write x rho x1. So if you, for example, observe all the xy values from the whole population, then you can calculate R naught. So that R will be called the population correlation coefficient. But practically we don't do that. So people are usually interested in testing a hypothesis like rho equal to 0 versus h1 rho xy not equal to 0. So this is making inference based on, this is tested using simple R, right? Sample correlation coefficient. There is a test in this case applied. It's also a kind of a t-test, because the critical value of that test is coming from a t-distribution. Right? So that standard t-test that people use to test this hypothesis require more assumptions. Right? That is one thing, is that this thing, that the correlation coefficient, the data must have come from something called a elliptical type of population. The population scatter should be elliptical or football shape. Right? Then only you can apply actually this test. More accurately, we say that if the XY values have a bivariate normal distribution, right? Not a univariate, bivariate normal distribution. Then only this hypothesis can be tested using the so-called t-test there, right? So therefore, generally it is better if sample, right? When you plot the sample also looks like a football shape. Of course, if you have a very small number of observations, this you cannot see that. You will see the football shape, even if the data came from the football shape population. Sample will not look like that if you have a small number of observations. So just to give you some idea about what you mean by bivariate normal distribution, here several bivariate normal distributions. These are like bells. These are the distributions. So the corresponding graphs here, and these ones are the contours. Right? අපි කැපුවොත් එහෙම මේ බෙල් එක එක ලෙවල් වලින් අපිට පේන්නේ මේ විදිහේ contours සමෝච්ච රේඛා කියලා කියන්නේ. ඒක සමෝච්ච රේඛා. ඒතර මේ විදිහේ population එකේ මේ වගේ නම් තියෙන්නේ හැඩේ ව්‍යාප්තිය. ඒ වගේ අවස්ථාවක when you get a sample from that kind of population, then of course the sample will have a football shape scatter. Right? So that is a requirement for if you want to carry out statistical tests like testing whether rho is equal to 0, testing rho is equal to 0 is equal to testing whether the two variables are independent. Right? Variables දෙක independent නම් තමයි rho බිඳුව වෙන්නේ bivariate normal distribution එකක් තියෙන වෙලාවට. Right? එතකොට I have seen in many research papers people when they carry out this test, for example, when they want to test whether rho is equal to 0, they carry out a t-test without checking whether the data have bivariate normal or not. ඒක සම්පූර්ණ වැරදි. ගාක් රිසර්ච් පේපර්ස් වල නිකන් දැන් ටෙස්ට් එක කරපු ගමන් p value එක කියලා එකක් දෙනවනේ අවුට්පුට් එකේ. ඒ p value එක 0.05ට වඩා අඩු නම් ඒගොල්ලෝ රිජෙක්ට් තීරණය කරනවා we reject test note. Right? Significance test එක කියලා තේ විදිහේ p value එක if the p value is less than whatever the alpha level then you reject. So in that case we reject that hypothesis rho is equal to 0 and then decide that there is some association in the population. But that will be valid only if we can assume that the joint distribution of x and y is bivariate normal. Right? ඒ ටෙස්ට් එක වැලිඩ් වෙන්නේ ඒ වෙලාවට විතරයි. ඉතින් ඕක හුඟක් අය දන්නේ නැහැ. හුඟක් අය දන්නේ නැහැ. ඔහේ නිකන් අර රෝ එකේ දෙන කම්පියුටර් එකේ දෙන p value එක විතර දිහා බලලා විතර ඩිසිෂන් එක ගන්නවා. ඉතින් ඒ p value එක නිවැරදි වෙන්නේ අර ව්‍යාප්තිය bivariate normal නම් තමයි. So the p value we interpret කරන්න ඉස්සර වෙලා before we interpret the p value we want to check whether that p value is valid, right? So in order to check whether the p value is valid we have to check whether the joint distribution is bivariate normal. So people don't do that part and then go and directly interpret the p value. In most of the research papers it's like that, right? Anyway, so that's one requirement for us to make inference regarding the correlation. Right? And other properties, we have discussed these things. They are unit free because it's the average of the product of standardized values. So this whatever the unit of x is, standardized values don't have units. Standardized values are unit free. This is unit free, this is unit free, therefore the average is always unit free. Right? So whatever the unit of x and y, R doesn't have a unit. And also if you for example transform your x value and y value using a linear transformation, right? So if you can calculate the correlation coefficient but between x and y, you will get some value. even if you calculate, say, the correlation between AX plus B and CY plus D, A and B, A, B, C, D are some constants, then the correlation coefficient between, say, this is X dash and this is Y dash, the correlation coefficient between X dash and Y dash is the same as the correlation coefficient between X and Y. So this is kind of shifting the values, and then this is scaling. So scaling and shifting doesn't affect the correlation. And then we discussed in the class something called SD line, which is also going to be related to the regression lesson. SD line. So when you have a scatter diagram, what do you mean by SD line? SD line is the line where the points will be if the correlation is perfect, if it is positive 1 or negative 1, right? So this line always goes through X bar, Y bar value, right? And then if you increase X value by X standard deviation of X, then and if you consider this one as Y, right? So all such points, and then there is 2xx and 2sy, 3xx and 3sy points. If you connect them, you will get the SD line. So that is the line that the points will be, where the points will be if the correlation was perfect. But of course, in practice, almost all the situations, we have r less than, absolute value of r less than 1, therefore the points will be around the SD line rather than they will be on the SD line. Right. So these are the SD lines when you have positive or negative relationships. Now, correlation measure the strength relative to the variability, not absolute closeness to the line. Right. So, in order to explain what this means, we can look at these two graphs, for example. Now, suppose, for example, we have some data, we have drawn the scatter diagrams, and suppose the scatter diagrams were like this. Right. In this case, notice that the scales are the same here. This scale and this scale is the same. This scale and this scale is the same. Right. So, of course, if you want to compare some two graphs, you have to produce the same the graph on the similar scales. Otherwise, you cannot compare anyway. Right. So, even if the scales are the same, now if you just look at this one, this is just x values and y values. This in another situation, x values and y values. Right. So, you might say that in this case there is a stronger correlation than this one. It looks like that, no? Right. But actually, if you calculate the correlation coefficient for these two cases, it's in both cases r is equal to 0.8. Right. So that's why we say we cannot actually judge or compare the correlations of two situations just by looking at the absolute values. Now these are actual values, right? Scatter plots of actual values will not give you a correct idea about the relative sizes of the correlation. Right? The reason here is actually here Sx is roughly the same, but Sy here, the variability in y is smaller here, 1, here 2.2. Right? That's why this graph looks more tighter, because the y values are more tight because the correlation is small. But if you, for example, for each of these xy values, you can calculate the standardized values. No, subtract the mean of x values from all the x values and divide by standard deviation. Subtract the mean of y values and then divide by the standard deviation. So we will have zx and zy for this graph, and similarly zx and zy for this graph. If you plot zy versus zx for those two situations, you will have this graph, these two graphs. Right. So it clearly shows that they have the same correlation. So therefore the correlation coefficient actually measures the or shows the association in terms of standardized values, not in terms of the actual or the absolute values. That is something that is useful because if you want to really compare by graphs, then rather than plotting the actual values, actual y versus actual x, it's better to plot the standardized values. Then it is easy to compare the correlations. Right. Now another thing is that usually we calculate these correlations based on the data coming from observational studies. So we already know that in observational studies, you cannot, even though there is a high correlation between two variables, it doesn't mean that there is a causation. One variable causes the other one. It just says there is some kind of association. Sometimes these associations may be real associations, or sometimes they can be spurious type of association. Right? For example, this spurious type of associations can arise due to several reasons. One reason is confounding. Right? If there is a third variable which is related to both of these variables, then you might look like see like there is a relationship between the two original variables. For example, here this is a well-known example: ice cream sales and drowning incidents. There were two data sets, number of ice cream sales and number of drowning in each month, and there was a very high correlation coefficient. There was a linear type of relationship, high. But we cannot say that when you eat ice creams, people are getting drowned. So that was only because of the high temperature, right? When you have high temperature, ice cream sales goes up. When you have high temperature, more people tend to go swimming, and many people can be drowning because of that reason. Right? So that's an association, spurious association caused by confounding variable in that case. And also sometimes if you plot x and y of two separate groups in the same graph, and then if you calculate correlation, you will see there is a high correlation, even though within each group there is no association between x and y, right? Like this. Right? So suppose this is x and y, this is the x and y scatter for one group, there is the scatter for the other. So within this group there is no relationship between x and y. Within this group also there is no relationship, but if you look at this one, it shows a very high correlation. If you just look at, for example, the average median value here, mean value, it looks like there is a high correlation. That is kind of again spurious relationship. So this kind of phenomenon has a name. It's called Simpson's paradox, right? Because if you look at individual groups, there is no association, but if you put them together, there is apparently a spurious relationship. Also, sometimes there can be, for example, positive relationship when you put them together. When you look separately, maybe in one there is a positive relationship, another group there can be negative relationship. That's also possible. Right? For example, if you consider two cases like this, in one like this, in the other one like this. So within this group is a positive relationship, it's a negative relationship, but if you put them together, one might think that it is a positive relationship. So that's called the Simpson's paradox. The other thing is that if you now consider several groups, for example, similarly, right? Several groups. And if you just calculate, instead of calculating the correlation of all individual observations, sometimes people get the average of this, and average of this. And so here you have xy point, xy point and xy point. So if you calculate the correlation between those ones, it may also give you a wrong idea about the actual correlation. Right? So this is an example like this. This is some data of the education level of some students and their individual incomes now. So these people came from 3 different areas, A, B, C. Right? So for example, this person came from area A, so his education level is whatever this amount, income is this. Right? And this person came from area B and his point is this. Right? So like that, if you now calculate, if you look at this whole picture, individuals, right? There seems to be a correlation, somewhat kind of moderate correlation. But if you, for example, calculate the average of all the A values, it will be here, right? Average education level and average income for all the people in A area, it will be here, and for area B, average point will be here. For C, average point will be here. So if you now consider only these 3 points and calculate the correlation coefficient, it's going to be somewhat stronger, larger value than this. Right? So this will give you a wrong idea, right, about the actual correlation. Right? So these are important, right? When you calculate the correlation, therefore you should not unnecessarily consider the averages and then take the correlations between averages, because it's going to be inflate usually or give you a wrong idea. Right. So this I have just mentioned those things. Correlation can be greatly affected by outliers, and correlation is based on group to average data may overstate individual level associations. And the numerical summary should never replace careful examination of scatter plots. That's what I said earlier. Right? Before we look at numerical summary like R, we must first of all explore the relationship graphically. So as far as R is concerned, we may say these are some good practices to apply. Always examine the scatter diagram before interpreting the correlation. Consider alternative explanations for observed association. Right? So don't try to interpret as causation at all most of the times, because they are not giving you causations. But sometimes the associations may be real, but sometimes they can be spurious. Therefore, you have to think of whether these have come from the real associations or whether they have been created by some other, like confounding variable or grouping and so on. Right. So I think that is the summary of the correlation coefficient that we learned. And then we discuss regression. Right. So regression, as far as regression is concerned, there are so many types of regressions. We discussed only one, right? That is the first very basic one, called the simple linear regression. Right? In simple linear regression, we try to model a linear relationship. If there is a linear relationship between some y variable and x variable. So that's what when we apply the simple linear regression. But more practical one is actually multiple linear regression. That is where we have one y variable and several x variables. Right? So in the simple linear regression, we consider the model y is equal to, say, alpha plus beta x plus some error always, because the points are not going to be on a line always. This is the line, right? But the points are a little bit above or below the line, therefore there is error. That's a simple linear regression model. But more generally, you will have y is equal to, say, alpha plus beta x1, say beta 1, say beta naught plus beta 1 x1 plus beta 2 x2 and so on, several beta k xk plus error. There can be several x variables, we are interested in seeing how they are related to y. Right. Now the word here, in this case, when you say linear, it actually means a straight line. Right. But here when you say, this is also called multiple linear regression model, multiple linear. In this case, the word linear doesn't mean a straight line, because it cannot be a line, no, it cannot be line. If you have only two variables, it is going to be a surface. Right? So in that case, we can interpret it as a flat surface. But when you have more than two variables, we only have to imagine, we cannot draw it. But the word linear here in this case really mean this equation is linear in terms of the coefficients. It doesn't mean straight line or not. Right? So in the word linear regression, usually the word linear means the model is linear in terms of the coefficients. For example, if you had a model like this, y is equal to say beta naught plus e to the power beta x. So this is not a linear relationship, because now if I expand, for example, this one using say Taylor expansion, this will be this part itself will be 1 plus beta x plus beta square x square divided by factorial 2 and so on. It's going to be a expression like this, where now you have beta square terms, beta cube terms and so on. So they are not linear in terms of betas. Right? So therefore that model is not a linear model. So we discussed only this one, simple linear regression. We apply that, of course, when we see a linear relationship. That means strong. In that case, linear also mean a straight line. So if the xy points are scattered around a straight line, then we can fit this kind of model. So in the linear regression model, what we generally do is we try to come up with a suitable model that describes the average value of y values for each x. Right? For a given x, there can be several y values that we have observed. We may have observed, get the observation at the same x, several x's, but y values will be different. So there is an average, and if you consider another x, then again there can be several y values at that x value, and then there will be average. So these average points, we are trying to draw a line through these average points. That the best line that goes through that like that is called the regression line. So the regression line is a smooth version of the graph of averages summarizing the overall linear trend. There are several methods that people apply to obtain the value, estimate for this and this, right? So here, this model we have written for the whole population. To consider any xy value in the population, we assume that y value is equal to a point on some straight line plus or minus some other term. Right? So generally, this is the assumed model for the population. What we want to do is estimate alpha and beta using a sample of data. Right? We have x1, x1, y1, x2, y2 up to x and y in n observations, and using those we get some suitable values for these. That is what we mean by estimate. So when you get suitable values, then you write down the model like this: y hat is equal to a plus bx. Right? Because now you have a straight line. So in that case, this value here is the estimated value of alpha. This value here is the estimated value of beta. And then y hat denotes the point on the line. Right? That is called the fitted value or the predicted value. That's what we try to get. In order to find out this estimate for alpha and this estimate B for beta, there are several methods, but most commonly used methods are method of least squares and method of maximum likelihood. In your book, they have briefly described about method of least squares. So in that, what we do is we try to, when you have a sample of data, we can draw a large number of lines that go through these points. Right? So if you consider any particular point, you can look at the distances between the predicted value according to that line and the actual y value. For example, if you consider this point, actual y value is here, the predicted y will be here. So there is a difference between those. So that is the error in our prediction. If you consider this point for the same line, this height is the actual y value and this is the predicted value. So this is the error. So like that, we will have n number of errors for a given line. Right? So what we do is we calculate sum of squares of errors. Right? Sum of squares of errors. So there, if there are n points, there will be n errors coming from a particular line. So for that line, there is a sum of squares of errors. If you consider some other line, for that line also, for the same observations, there will be a sum of squares of errors. Right? So like that, you can think of considering all the possible lines that go through these points. And for each line, there will be a sum of squares of errors. And then it's like selecting the line that gives you the minimum sum of squares of errors. Right? One line there will be that gives you the minimum sum of squares of errors. That is what you call the least square regression line. Right? So, but practically we don't calculate sum of squares of errors for each possible line. If we go to do that, we will have to do it million times. What we do is mathematically we find out by considering the error like this, we can write down error is equal to y minus alpha plus minus beta x. So what we will be looking at is sum of squares of errors. So we look at, for example, this quantity I from 1 to n yi minus alpha minus beta xi square. So we minimize mathematically this quantity with respect to alpha and beta. Right? So we minimize this quantity mathematically with respect to alpha and beta, and then so you have the first derivative of this quantity with respect to alpha, first derivative of this quantity with respect to beta, equate both to 0, and then solve for those two values. Then the values that we get are denoted by A and B, right? So those are the estimated values. These are all least square fits. Right? So that is the usual procedure that we apply to find out this A and B, or estimate alpha and beta.
So you can get alpha plus beta x, right? Because when you subject error, you get.
Yeah, sorry. You mean here?
Yeah, and there's a.
Yeah, there is. So that's the method of least squares, and the one that we get, we can get a mathematical formula for those estimates. We will see that B that we get from that is, we can write down as R times SD of y divided by SD of x, where R is the correlation coefficient. And we can show that A is equal to y bar minus beta times x bar, where y bar is the mean of y values and x bar is the mean of x values. So we can easily derive those two expressions. And then our fitted model is written usually like this. In that case, we write down y hat usually to denote that is the predicted y or fitted y, usually we say a plus bx. For this, there is no error term because we predict the y value by the value on the line. So b is the slope of the fitted line, and intercept is a. So we can get some idea about v actually has a practical meaning always. What is the meaning? That is the value. If you increase x by 1 unit, right? If you change x by increase x by 1 unit, how much will be the change in y on average, right? Because if you it's not going to be the same amount, but on average y will be changed by certain amount. That value is actually v, right? So that is the slope, right? In any straight line, that is how you explain. But in mathematics, it's just how you define, how you explain it is what is the increase or decrease in y if you increase x by 1 unit. In there, we don't use the word average. Mathematics will explain don't average කියලා වචනේ නැහැ. ඒක තමයි කොච්චරකින් y වෙනස් වෙනවද x එකකින් වැඩි කරොත් කියන්නේ. ඒතර y දාන වැඩි වෙනවා නම් ඒක ධනාංගයක්, y අඩු වෙනවා නම් ඍණාංගයක්. Now method explain කරනකොට you have to say it is the average change in y if you increase x by 1, not the change in y. Change in y is different, right? So therefore we can get an equation after putting a and b into this line. Y hat will be y bar plus r times dy divided by s dx times x minus x bar. So for a given x, therefore, we can easily find out the predicted value y. Just put the value, given value x here. All the other values are coming from the data. So you can get the predicted value. Now, I forgot to mention that two names, right? Especially in regression situation, you use the two words. Sometimes people call dependent variable and independent variable. Right? Y is called the dependent variable and x is called the independent variable. Right? Or more correctly, I think y is now called the response variable. Y is the response variable, x is the explanatory variable. Explanatory variable. Right? So you have to select in a given situation. You have to select which variable out of the variables you have, which variable is going to be the response variable, and the other one, which variable is going to be the explanatory variable, is selected. How do you select? If you want to predict some value, right? Predict the value of some variable, that variable is the response variable, right? So if you are using the other variable to predict the response. That's how you select which variable should be the response and which variable should be the explanatory variable. Right? But as far as the correlation is concerned, if you are just interested in finding the correlation, it doesn't matter which variable is independent or which variable is explanatory, because the correlation between x and y is the same as correlation between y and x. It doesn't matter which one is y and which one x. But in regression, it's important. Especially when you are trying to predict something, the variable that you want to predict has to be the response variable. Right. So graphically, in the book they have explained this regression line in terms of this, right? So you have already something called the SD line. SD line goes through x bar, y bar, right? So SD line, and if you draw this regression line, it will be, for example, if it has a positive slope, it is also going through x bar, y bar, but it will be like this. SD line, if you increase x by sx amount, y value will be, this value will be increased by this height will be s of y, right? That is what the SD line is. Right? So you can easily get the SD line by connecting average point and this point. But the regression line, if you increase x by sx amount, this height will be only r times sy. It's not increased by sy amount, it will be increased by r times sy, and usually r is less than 1, in this case positive, but less than 1. Therefore this amount that is increased up to the regression line is less than the increase in the SD line. Right? So it will, therefore, on this side the regression line will be below the SD line, on this side it will be above the regression line. On the other hand, if you have a negative relationship, it will be the other way around. Right. That's what this one says. Regression line gives you the best linear prediction of the response variable. Actually, when you say best linear prediction, it's not about individual points, overall, on average, right? Because what we are doing is minimizing the sum of squares of errors, not the individual errors, right? Sum of squares of errors. Right? So best linear prediction in terms of average errors. This regression line always goes through x bar y bar point. So the regression line is flatter than the standard. Right? This is flatter than the SD line. Right. Next thing is there was a word called regression effect. Regression effect and regression fallacy. So I have tried to explain that. This was first discovered by Garrison, who introduced regression. He called this regression effect, he called this regression toward mediocrity. That's what he called it. But now many people call it regression towards the mean or regression effect. Regression toward the mean or regression effect. This is something. This is a statistical effect. Actually, statistical phenomenon rather than a causal or practical effect. What we mean by this is, if you collect some data in a data set generally, if you consider extremes, right? Extremes, for example, let's consider value observations with some smaller. This is x bar y bar, for example, point here, right? This is x bar, this is y bar. So if you consider some small x values, so large x values, for a given small x value, there will be several y values, and for a given x value here for large x, again there will be several y values. What they talk about is that if you consider x and y, for example, if x is small for some value, generally its y values are going to be larger than the usual what we expect. And similarly for these values, right, x values එක large වෙනකොට y values එක වෙන්නේ අතරම average එකට බර වෙනවා. For x values දැන් මෙතන x values තියෙනවා දැන් මේ average එක තියෙන මේ පැත්තට. එතකොට මේකේ average sorry for a given x average y value තියෙන්නේ මෙතන. Right. එතකොට මේ x වල මේ x කියන එක small වුණාට ඒකේ y values small වෙන්නේ නැහැ. බොහෝ වෙලාවට ඒකේ a values මේ average එකට මේ පැත්තට බර වෙනවා. Right? That's what you call the regression towards the mean. Right? උදාහරණයක් ගත්තොත් මෙහෙමයි ප්‍රායෝගිකව ගත්තොත් දැන් let's consider two exams, midterm and final exam. Right? So those who get less marks in midterm tend to get little higher mark than in the final than the midterm. Those who get very high marks in the midterm tend to get little bit more, less marks, not very less, but smaller than what we expect in the final. right? Average එක පැත්තට බර වෙනවා. right? අර ගොල්ලෝ දැන් අර ධන පැත්තේ අර average එකට උඩින් ඉන්නේ වැඩිින් දකලුගත කට්ටිය mid term එකේ ඒගොල්ලෝගේ final එකේ බොහෝ වෙලාවට ඒගොල්ලෝ average එක පැත්තට බර වෙනවා. වැඩිපුර දිනෙක එක පැත්තට. මොකද සාමාන්‍යයෙන් ඕනම data set එකක average ඕනම මේ group එකක තමයි මේකේ data පොදුවේ ගත්තොත් එන්නේ average එක පැත්තට තමයි බර. right? ඒතර අර group එකේ ගත්තාම මේ වැඩියෙන් තියෙන group එකෙත් x අගේ එතනදී වැඩි වෙලා තියෙන්නේ random error එකක් නිසා x අගේ ගොඩක් වැඩි වෙලා තියෙනවා. නමුත් ඒ group එක තුල ගත්තාම ආයසරයක් එතනින් වැඩි ප්‍රමාණයක් average එක පැත්තට බලන average y පැත්තට. ඊට පස්සේ extreme මේ පැත්තේ x එකක් extreme වෙලා තියෙන සමහරට ආයේ with a very small probability. නමුත් ඒ x එක සහිත y අගයන් ටික සැලකුවොත් එimhe ඒ y අගයකින් ආයසරයක් දැන් ඒකේ x අගේ අඩු හින්දා y අගයත් අඩු වෙන්න ඕනේ සාමාන්‍යයෙන්. නමුත් එහෙම අඩු වෙන්නේ නැහැ. ඒක average පැත්තට ආයෙ බලන්න. average එක පැත්තට උඩට යනවා. y අගේ. So that is something that is happening usually. That is due to the something called central tendency, right? Given for a given data set, most of the observations are going to be towards the center. That is generally happening. So the extreme වලදී ඒක වෙනවා. So that's what we call the regression effect. Regression effect. So ඒක regression effect කියන එක කවුරු හරි ඉන්ටර්ප්‍රිට් කරනවා නම් ඒක මේ cause යම්කිසි මේ දෙයක් නිසා ඇති වෙච්ච ප්‍රායෝගික දෙයක් කියලා. අන්න ඒ explanation එකට අපි කියනවා regression fallacy කියලා. Right? That's explanation is called the regression fallacy. Interpreting this purely statistical effect as a genuine causal change leads to regression fallacy. Right? I think. So these are some general things that you already know. Regression can be applied for the observational studies, and that's where we apply usually. So even if there is a very strong regression line, right, there are methods to find out how good the regression line fit is. There is something called goodness of fit test, right? එතකොට යම්කිසි මේ මොඩල් එක ෆිට කරපු මොඩල් එකේ ෆිට්නස් එක ඉතාම හොඳ වුණත් ඒකෙන් කියවෙන්නේ නැහැ එතන ඇත්තටම causation එකක් තියෙනවා කියලා x y අතර. That only shows that there is a high association, and we can predict the y values with more accuracy using x values. That is what we call, right? Prediction එකේ මේ strength එක තමයි එකකින් කියවෙන්නේ. එකකින් වෙනත් දෙයක් කියවෙන්නේ නැහැ. Association එක තිබුණාට causation එකක් තියෙනවා කියලා කියවෙන්නේ නැහැ. ඊට පස්සේ තව එකක් තමයි දැන් predict කරනකොට if you have fitted the model using this scatter, and you should not predict a value for y or this kind of x, right? When you predict also you have to use you can predict using this model only for a value in this range, because we don't know what the relationship here is. It might be going like that and going like this, right? So if you use this line, it's completely going to be wrong. So extrapolation beyond the observed data range can be misleading. Right. Now, as far as fitting the model is concerned, we can fit the model using the least square method. But more than fitting the model, sometimes we want to do again some inference regarding this thing. For example, we have assumed that y is equal to say alpha plus beta x plus error. This is the assumption. So then කෙනෙක් අහන්න පුළුවන් is there a actual relationship between x and y, right? ඇත්තටම x and y මේක දැන් මේක නම් එක අතට නෑ මොකද අපිට correlation එකකින් මේක කියන්න පුළුවන්. නමුත් multiple linear regression එනකොට y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on up to beta k xk plus l. Right? So we use this kind of model generally when we probably think that variable y may or may not be associated with x1, x2, x3 and several things, right? Maybe from some research, previous research, they have found out in some other country, some y variable is associated with several variables. So, but it may not be the same for Sri Lanka also. So, somebody wants to find out what is the situation in Sri Lanka. Out of these variables that they have found, which variables are associated with y in Sri Lanka. So, in this case, we cannot calculate the correlation between y and x1, y and x2, y and x3 and so on separately. It's not going to give you the correct idea about association. So what we do in that case is, if there are several variables which may be associated with y, we fit a model like this and then test whether this beta 1 in the population is equal to 0 or not. So we test whether, carry out the hypothesis H0 whether beta 1 is equal to 0 or H1 beta 1 not equal to 0. එකෙන් ඒක beta 1 සමානයි බිඳුව කියලා අපිට ආවොත් ඒකෙන් කියවෙන්නේ මොකද්ද x1 කියන variable එක y predict කිරීම සඳහා වැදගත් නැහැ කියන එකයි ඒකෙන් කියන්නේ. Right. Similarly, we can test about whether beta 2 is equal to 0 or not. We can test whether beta k is equal to 0 or not. Right. ඒතකොට ඒකෙන් පුළුවන් අපිට හඳුනා ගන්න මේ අපි මුලින් සලකපු variables වලින් which variables are really important in predicting y. Right. මොකද අපි සාමාන්‍ය මොඩල් එක variables දැන් කවුරු හරි කියලා දෙනවා variables 25ක් විතර මේකට වැදගත් වෙනවා කියලා. අපිට ඒක predict කරන්න නම් මේ variable 25ම mind එකේ දත ගන්න එපා. නමුත් අපිට ඒගොල්ලන්ගේ මොඩල් එකෙන් කරන තරම්ම හොඳ දෙයක් කරගන්න පුළුවන් නම් variable 5කින් that's much better. Right? We have to measure only, get the data only from 5 variables because getting data is not easy. Right? So අපිට වැදගත් වෙනවා මොන variables ද ඇත්තටම important වෙන්නේ if you want to get a good prediction. Right? So therefore we need to identify the most important variables in predicting y. ඒතර ඒ වගේ වෙලාවක මේක තමයි කරන්නේ. මොඩල් එක fit කරනවා, fit කරලා බලනවා මොන coefficients ද non zero coefficients තියෙනවා. So this is part of inference. So මෙතනදී statistical test එකක් මේ apply කරන්නේ. So the statistical test, there are some assumptions, required assumptions. So the assumptions මේක විතර නෙමෙයි මෙතෙන්ටත් පොදුයි. So what are the required assumptions to make inference regarding a regression line? So I will briefly explain what those assumptions are to necessary to make inference. Right? මේක අවශ්‍ය වෙන්නේ අර estimates ගන්න පුළුවන් නමුත් ඔය estimates වල accuracy එක අදී දේවල් ගන්න ගියාම වැදගත්. So the first one is these x1, y1, x2, y2 and so on. When you have this x and y in, we have to assume that these observations are independent. Right? That is one assumption. The other assumption is about the distribution, right? So if you have x and y values for a given x, when you observe, you may have several y values, but of course these values have come from a large set of y values in the population, right? In the population, for example, if you look at the height and weight, එකම උස තියෙන පුද්ගලයෝ ඕනතරම් ඉන්නවනේ population එකේ. ඒත් ඒගොල්ලන්ගේ විවිධ weights තමයි තියෙන්නේ. ඒතකොට ඒ weights වලින් කීපයක් තමයි මෙතන ඇවිල්ලා තියෙන්නේ. එතකොට අපේ assumption එක තියෙන්නේ population එකේ මේ දෙන ලද x එකකට තියෙන y values normally distributed කියලා උපකල්පනයක් තියෙනවා. In the population. ඒතකොට ඒක අපිට test කරන්න පුළුවන් මේ sample එකේ දත්ත පාවිච්චි කරලා. Right? So similarly for a given x, we assume that in the population y values are normally distributed. For a given x, y values are normally distributed. එතකොට මේ normal ව්‍යාප්තියට යම්සි mean එකක් තියෙනවා. මේ normal ව්‍යාප්තියට යම්සි mean එකක් තියෙනවා. මේ normal ව්‍යාප්තියට යම්සි mean එකක් තියෙනවා. අපි හිතනවා මෙන්න මේ means ආසන්න වශයෙන් straight line එකක් මත තමයි තියෙන්නේ. එතනින් තමයි linear model එක එන්නේ. Right? Linearity assumption. Right? The other one is we assume that the variance, if you talk about the normal distribution, there is a mean that we talk about and a variance. Right? So එකක් තමයි අපි හිතනවා මේ means තියෙන්නේ straight line එකක් මත ආසන්න වශයෙන්. Right? They are on a straight line. That is called the linearity assumption. The other assumption is that we assume that variance of this normal distribution is the same as the variance of this normal distribution and the variance of this normal distribution and so on. So they have the same variance. That assumption has a particular name. It is called assumption of homoscedasticity. Homoscedasticity or equal variance. Right? Homoscedasticity is a Greek word. So those are the main assumptions that we have to make in order to make the inference. Right? Independence of these pairs of observations, normality of y values for a given x, the means have to be on a straight line. That is called linearity assumption, and the homoscedasticity assumption is that variances for a given y value is the same as variances of y values for a given x is the same as the variances of y values for some other x. Like that for all x is the same. So these assumptions හරිනම් පමණයි අපිට අර අදාළ ටෙස්ට් දාන්න පුළුවන්. මේ ටෙස්ට් ටික දුන්නේ මේ පොතේ. නමුත් ඒවා වැදගත්. right? එතකොට ටෙස්ට් දාන්න නම් මේ assumptions හරිද කියලා බලා ගන්න ඕනේ. එතකොට ඒක බලා ගන්න සාමාන්‍යයෙන් අපි කරන දෙයක් තමයි මෙන්න මේ residual කියලා දේ පාවිච්චි කරනවා. We use residuals to check whether these assumptions are satisfied. Right? So we carry out something called residual analysis to check whether the assumptions in the regression are reasonable. අපි බලනවා මේ විදියට normal කියලා ගන්න එක reasonable ද, homoscedasticity assumption එක reasonable ද ආදී වශයෙන්. So what is the residual? Residual කියලා කියන්නේ the difference between the fitted y minus the observed y. Now observed y minus the fitted y. Oops. Right? So then මෙතන මේ observation එක මෙතන මේ x එකට මෙතන x y එක දෙකක් තියෙනවා. මේ y එකට දාන residual එක කියලා කියන්නේ මෙන්න මේ උස minus මේ උස. So that is a positive residual. ax එකට මෙතන y එකක් තියෙනවා. මේ y එකට දාන residual එක කියලා කියන්නේ මේ උස minus මේ උස. Right? So මේකෙදි residual එක negative. Right? So the residual is equal to observed value minus the fitted value. Fitted value is the value on the regression line. Observed minus the fitted. Observed y minus fitted y. So that is y minus y hat. Y is the observed value. Y hat is the fitted value. Therefore, residuals can be positive or negative. If the actual value is above the line, then the residual is positive. Otherwise, it's negative. Right. So for each pair of observation, each xy pair, then there is a residual. Right. For each point, there is a residual. Now, when we plot these residuals, for example, for this x value, there are two residuals. If I plot those residuals versus that x value, right, versus x versus this residual, you get this graph, residual versus x, right? That's called the residual plot. Residual plot. So when we residual plot we use the residual plot to check the reasonability of our assumptions. Keep them. එකක් තමයි අපි බලාපොරොත්තු වෙන්නේ අර මොකද්ද linearity assumption එක satisfy වෙනවා නම් සහ homoscedasticity assumption එක satisfy වෙනවා නම් we expect this kind of graph, right? බිඳුව වටා සම්මිතික මේකේ තියෙන x අක්ෂය මෙතන තියෙන residual. The residual should be randomly scattered and without any pattern. Residual should be randomly scattered without any pattern in a horizontal band like that. එහෙම තියෙනවා නම් ඒකෙන් කියවෙන්නේ ඒකෙන් අපිට අදහස් වෙනවා අර මොඩල් එක ඇත්තටම ලීනියර් මොකද අපිට මේ ලීනියර් එකකින් අඩු කරලා නරන් තියෙන උතර දැන් ෆ්ලැට් වෙන්න ඕනේ ඒක නිසා සහ කිසිම පැටර්න් එකක් තියෙන්න බෑ පැටර්න් එකක් තියෙනවා නම් ඒ කියන්නේ ලීනියර් මොඩල් එකේ මේ සුසුම වෙනත් මොඩල් එකක් කියන්නේ දැන් ලීනියර් ටික අයින් කරලා තියෙන්නේ අඩු කරලා හැබැයි තවදුරටත් පැටර්න් එකක් තියෙනවා කියන්නේ x වල තවත් වෙන මොකක් හරි ෆන්ක්ෂන් දෙකක් තියෙනවා කියනවා ඒකට ඒක හරියන්නේ නැහැ so if there is only a linear relationship in terms of x we expect the residual plot to be like this. That is the expected residual if the linear assumption is satisfied. ඒ වගේම homoscedasticity assumption එකත් ඒකෙන්ම බලා ගන්න පුළුවන් මේ variability එක roughly the same. Variability of y value වල variability නේ අපි homoscedasticity එකකින් බලන්නේ. If the y values for given different x's are the same then residuals will have the same variance also. ඒක නිසා ඒකත් මේකෙම බලා ගන්න පුළුවන්. එතකොට මේ වගේ මොන හරි આવොත් එහෙම that indicates something wrong in our assumptions. Our assumptions are not reasonable. Right? Not good. එතකොට මේ වගේ plot එකක් આવොත් මොකද්ද අපි සාමාන්‍යයෙන් කියන්නේ එහෙනම් තියෙන relationship එක ඇත්තටම linear relationship එකක් නෙමෙයි. ඒක ප්‍රමාණවත් නෑ. එක්ක අපි තව quadratic term එකකුත් ඇතුල් කරන්න වෙනවා. කියන එකයි කියන්නේ. X maybe we have to update our model like alpha plus beta x plus some other gamma x squared is required. Linear model is not enough. මේ වගේ එකක් આવොත් ඒකෙන් කියවෙන්නේ variability එක දැන් සමාන නැහැ. එන්නේට වැඩි වෙනවා. එහෙම නැත්නම් අනිත් පැත්තට එන්න පුළුවන්. right? funnel shape එකක් වගේ આવොත් එහෙම නැත්නම් variability එකේ ලොකු වෙනස්කම් තියෙනවා නම් x අගය මත ඒකෙන් කියවෙන්නේ අර homoscedasticity assumption එක reasonable නෑ. ඒකට කියනවා අපි heteroscedastic කියලා. heteroscedastic. එතකොට එතකොට ඒ වගේ වෙලාවට කරන්න පුළුවන් දේවල් තියෙනවා. ඉතින් ඒකත් මේ පන්තියේ කතා කරන්න නිසා මම කතා කරන්නේ. බොහෝ වෙලාවට අපි කරන්නේ ඒ වෙලාවට y අගය transform කරනවා. y වෙනුවට log y වගේ දෙයක් පාවිච්චි කරලා මොඩල් එක ආයෙ ෆිට කරනවා. ඒවා තමයි සාමාන්‍යයෙන් කරන්නේ. එතකොට මෙතන මේකේ තියෙන ප්‍රශ්නේ තියෙන්නේ මෙතන කැමති පැටර්න් එකක් තියෙනවා. right residuals කියන එක පැටර්න් එකක් තියෙනවා. මේක horizontal නෙමෙයි බෑන්ඩ් එක. උඩට යන බෑන්ඩ් එකක් නෙදී. ඒතකොට පල්ල සමාන වුණාට ඒ කියන්නේ homoscedasticity එක වෙන තිබුණට හරියට right model එක linear නෑ කියන එකයි ඔයින් කියන්නේ. So like that we can find out we can check the reasonability of the assumptions. ඊට අමතරව residuals the normal කියන assumption එක මෙතන check කරන්නේ. ඒක normal ද කියන එකත් අපිට බලන්න පුළුවන්. There are some tests for normality. So we can check if the y values for given x's are normal then the residuals have to be normal also. So we can check whether they are normally distributed also. So this therefore in regression this residual analysis is a very important part. Right? So මේකත් අර correlation එකේ මම කියවා වගේ multi මොකද්ද bivariate normal ද කියලා check කරන්න නැතුව නිකන් p value එක දිහා බලලා උත්තර ගන්නවා වගේ තමයි මෙතනත් regression ගොඩක් researchersලා මේ part එක කරන්නේ නැහැ. කරන්නේ නැතුව කෙලින්ම යනවා inference වලට ගිහිල්ලා ඔහේ inference කරලා ඒකේ තියෙන ඒකේ test කරපුවා වෙන p value දිහා බලාගෙන එක එක දේවල් කියනවා. සමහරට මේ assumption එකක්වත් satisfy නොවෙන්නත් පුළුවන්. ඒකට අර දීලා තියෙන p value කම්පියුටරේ ගන්න නැහැ නේ කම්පියුටරේ ඔය check කරන්නේ නැහැ මේ assumptions check කරන්නේ නැහැ. ඒතර කම්පියුටරේ just output එකක් දෙනවා formula වලට අනුව calculate කරලා p values දෙනවා but those p values may not have any meaning if the required assumptions are not reasonable. So therefore it's very important to check whether the assumptions are satisfied before we interpret our p values. In any situation is like that. Right. Pretty break that down.